And then and hopefully the screen should be showing now. Okay, so thank you for the invitation to speak today. I'm sad that I'm not able to come in person. I always have a wonderful time when I visit. This talk is actually motivated by a conversation I had with April when I was visiting Texas State recently for a conference. And what I want to do today is I want to talk a little bit about how I find some of the problems I work on. And so, as was mentioned, I have published a tremendous amount with a large number of students. I am very fortunate to have a good set of colleagues. Everyone can be a colleague. Everyone can ask a good question. I think the youngest colleague on this talk is going to be somebody who is just barely in double digits for age. And so what I want to do is I want to talk about something that began when my kids were very young, 2 and 4, and has led to a lot of really interesting mathematics that I've used both in research as well as in teaching. Okay, so the world is rapidly changing. And so what you have available is very different than what I had available when I was a kid. And you want to try to figure out, how does this affect what you're going to be doing as a mathematician? You know, what skills are you learning in classes? What skills are you learning in summer research programs? How should you attack problems? How should you take advantage of the ability to gather massive amounts of data and use that to influence what you're doing? And so I try to encourage everybody to ask as many questions as you can. I encourage people to learn how to program so that you can gather data, so that you can simulate and get a sense of what you might want to conjecture. I love playing games. And so I like to use games frequently as a springboard to mathematics. I'm going to be supervising a lot of students this summer on game-inspired problems. And then this began with my children, Cameron and Kayla. I think we finally published the papers when they were 10 and 8, but it actually began when they were 4 and 2. And so we don't really need too many prerequisites to do this problem, which is nice. So basically, I just need people to understand, what is a logarithm? What are exponents? What are logarithms? And then, some basic combinatorics. N factorial is the number of ways to order n people when order matters. N choose k is the number of ways to choose k people from n when order doesn't matter. And then one of the things that we're going to be using is some things related to Pascal's triangle. So hopefully everybody has seen this. I'll just quickly review a few things and then just share maybe an interesting pattern that you haven't seen before. So the kth entry in row n in Pascal's triangle is n choose k. And you can go on. It's an interesting question to try to explore, how rapidly do these numbers go, to try to explore what kind of properties and hidden structures are there in Pascal's triangle. And that's one of the themes for the talk today, is that there's often structure lurking all around you that you may not have noticed yet, and trying to find what's the right way to look at things, what's the right questions to ask. So for example, if we only look at Pascal's triangle mod 2, so we just care is a number even or odd, and we black out all the numbers that are odd, we see a very interesting structure emerge. And there's actually a fractal structure here. You can see the even numbers are forming triangles on the inside. And then just going, more and more iterations, it's not too bad to write a computer program to do this. I actually made a little YouTube video because I couldn't find a good one online and I wanted it for my students. So I encourage you to play a little bit with this and see some of the structure there. And again, the reason I'm bringing this up is that there's a lot of hidden structure everywhere around us. And the goal is to try to figure out, how can we ask good questions that will illuminate the hidden structures? Okay, so now the main part of the talk is the M&M game. So when my son was 4 years old, he asked the following question: if you're born on the same day as someone, do you die on the same day? And this is a terrific question. And when you're young, you don't really appreciate how important it is to ask good questions. After a while, you've all taken math classes, you're all competent, you all know how to do so many things, but you need to know what to try to do. And so mathematics lives on questions and conjectures. And so how do you explain randomness to a 4-year-old? Well, I'm fortunate. My wife is an identical twin. Oh, look, I just shot mom's twin sister. She's dead, but mom's alive. No, okay, you can't explain randomness, to a 4-year-old and a 2-year-old like this. So can we come up with another way? And so the way I came up with was the M&M game. And so the way it worked is everybody started off with k M&Ms. We did 5, And we went 1, 2, 3, toss, and we all tossed a fair coin at the same time. And if the coin came up as a head, we ate an M&M. And if it came up as a tail, we didn't. And you kept tossing until all your M&Ms were gone. So a little audience participation. Can anybody give me a natural question to ask about this game? So can someone give me a good question to ask about this game?
How many tosses does it usually take for you to lose all your
Excellent,
M&Ms?
excellent question. How long do you think the game is going to take? Or even more generally, do you expect the game will eventually end?
Yes.
Excellent, and you are correct. Any other questions? So there's a lot of questions you could ask. One question is, how likely is it for a tie? You know, the original question from my son was, if you're born on the same day, will you die on the same day? So how likely is it that two people will eat their last M&M at the same time? And then once you learn how to solve a problem, the next thing is to try to generalize. What if we had more people? What if we had a biased coin? And if time permits, at the end of the talk, I will talk a little bit about a generalization that April and I came up with less than a month ago. And so let's gather some data. And so what I did is I had my computer, play the game, and I calculated what's the probability of a tie. And with one M&M, it was 33%. With two M&Ms, it was about 19%, and so on and so on and so on. When you look at a picture like this, it's kind of hard to see the pattern. So the first time I gave this talk was at the 110th anniversary of a math association in Massachusetts. And so I went all the way up to 110, and I asked the audience, can you try to predict where will we be in 110 years? Where will we be if we had 220 M&Ms? What would you guess the probability is? Now, with 110, it looks like it's a little bit less than 5%, but it's kind of hard to see what that curve looks like. And so is anybody brave enough to try to guess what they think the probability might be at 220? I would not be brave enough. So it's not just what data you have, it's how do you present data in a way that's useful. And so we want to gather the data, but we have to figure out what's the best way to present it. And for something like this, I can't really look at this and predict what's going on. This is not a curve I understand. But one of the things you've hopefully learned is logarithms. There's a reason we learn logarithms. There are two reasons for logarithms. One is it allows you to look at data that spans many orders of magnitude. And another is it can convert nonlinear relationships to linear relationships. This should look a lot like a straight line. And we can try to find the best fit line through this. And if we do, we can calculate what's the log of the probability of a tie. We get a formula for that. And then we can substitute in when k equals 220, and we get about 0.01274, but the actual answer is about 0.0137. So it's not horrible, but it's not terrific. If you look at the line, does this look like a good straight line? For all the data or for some of the data? Can somebody tell me if they think this is a good straight line for all the data or some of the data? Does it go through all the points, or does it go through some points more than others? What do you think?
I think it.
Yes?
That near the top, they're not so straight, but when they get like lower and lower, then yeah.
Excellent, excellent. It seems to be going through more of the points further down. Maybe it takes a while for the limiting behavior to kick in. Maybe the first few points, things haven't quite settled down yet. So rather than looking at all the values, maybe the first few values are misleading us. Let's look at just the data from 50 to 110. And now when I try to look at the best fit straight line, I'm going to see if I can zoom in. You can see that best fit line is going almost perfectly through all the points. It's incredible. And now when I try to calculate the probability of 220, I get 0.01344. The correct answer is 0.01347. That's terrific. And so there's a really good lesson here about it can take a while for the limiting behavior to kick in. All right, so now, before proving the actual formula for the M&M game, I want to talk a little bit about another way of looking at problems, which is going to be very useful. And there's a wonderful idea behind this that appears in a lot of problems in mathematics and economics. And so I'm old, so when I think of basketball players, I know the Celtics have done very well this year. I think of the 1980s, I think of Larry Bird for the Celtics and Magic Johnson for the Lakers. And we're going to imagine that they play a very strange game of basketball. Whoever makes a basket first wins, and they alternate shooting. And we will assume that they always have the same probability of making a basket. It doesn't matter if Bird has shot 5 times, 100 times, 1,000 times. He has a fixed probability of making a basket. Same for Magic. And so we want to calculate what's the probability that Bird wins. Well, let's say Bird always gets a basket with probability P, Magic gets a basket with probability Q. I want to calculate the probability Bird wins. So can somebody tell me what's the probability that Bird wins on his first shot? So Bird shoots first. He always gets a basket with probability P. Magic always gets a basket with probability Q. So what's the chance that Bird makes his first basket? One of the students in the audience, can you help me out?
Probability P.
Probability P, excellent. So we're going to break into cases. So Bird wins on his first shot with probability P. What's the probability Bird wins on his second shot? So his probability P on his first shot, what's the probability that he wins on his second shot? What must happen for that to hold? So you got the answer on one shot. What must happen if Bird wins on his second shot?
Probability P times probability P.
Not P times P. If Bird's going to win on his second shot, what must happen on Bird's first shot? It must be
the complement.
The complement. So he must miss. So it's 1 minus P. And then what must Magic do on his first shot? Magic has to miss. That's a 1 minus Q. And then Bird gets it. So it's 1 minus P, 1 minus Q times P. And then for Bird to win on the third shot, he misses, Magic misses, he misses, Magic misses, and then he hits. And so we see that if Bird is going to win on the nth shot, he's going to have n misses, Magic is going to have n misses, and then Bird's going to hit the last basket with probability P. So if we want to calculate the probability that Bird wins, just to make the algebra a little bit nicer, let's let R be 1 minus P times 1 minus Q. Then the probability that Bird wins is just he wins on the first shot, which is P, plus he wins on the second shot, R times P, plus he wins on the third shot, R squared times P, and so on. And we see that it's just P times 1 plus R squared plus R cubed, and so on. So this is the famous geometric series formula. And so if we know the geometric series formula, then we can answer the question right now, what's the probability Bird wins? What's nice is we can actually use this as a way to prove the geometric series formula. And in doing so, we're going to learn a really nice math concept. So we showed that the probability that Bird wins is P times the geometric series. Another way of looking at it is, what's the probability Bird wins? Well, Bird could win on the first basket, which happens with probability P. Or if Bird misses and Magic misses, so this is the key of the argument. What's the probability that Bird wins from this point onward, given that both he and Magic have missed? Is anybody brave enough to try to answer this? So they've both missed. What's the probability Bird wins from this point onward?
That's X again.
It's just X. X is the probability that Bird wins when Bird is shooting. So we get an infinite sum has now been reduced to a finite sum. And so if we just do a little simple algebra, we can solve X. X is just P over 1 minus R. And then since X is P times the geometric series, we've just proved the geometric series formula. So this is called a memoryless process. Once they've both missed, it's like we're starting the game all over again. And this is an incredibly powerful idea in mathematics. So we can actually circumvent this algebra, we can bypass an infinite sum and make it a finite sum. So let's see how this can help us with the M&M game. And we're going to get to a closed form expression, and we're going to, see how we can use this to write down very nice formulas and bypass, again, terrible infinite sums. So here is the overpower with algebra approach. This infinite sum is the probability that if each person starts with k M&Ms, that the game will end in a tie. And so we've got our binomial coefficients, we have an infinite sum. The question is, where did this come from? And once we have this, can we actually evaluate this? How do you get that this is 1/3 when k equals 1? Well, one way to evaluate this is to know some advanced mathematics. So for the professors in the audience, I will just say that this simplifies to the special value of a hypergeometric function. But again, you have to know how to convert it like that. That's not a good way to approach this problem. So let's try to give a motivation of where this formula comes up. There's 4 possibilities. Either both eat an M&M, just Cameron eats, just Kayla eats, or neither eats. And each of these happens 1/4 of the time. And so when you go through this, if you want the game to end after n tosses, then n has to be at least k, because you have to have k M&Ms eaten. And so of the first n-1 tosses for Cameron, he has to eat exactly k-1 M&Ms. That's the n-1 choose k-1. And then since it's a fair coin, that's the 1/2 to the n-1. So you can justify this formula with a little bit of work, but this is not a pleasant formula to analyze. But let's use the lesson we just learned from the hoops game. Instead of saying that there's 4 possibilities, there's really only 3 possibilities. If we got 2 tails, neither ate an M&M, so we might as well just pretend that that toss doesn't happen. Let's only look at tosses where there's at least one head. So now there's 3 possibilities, and each one occurs just 1/3 of the time. So I'm not going to go through the algebra, but you can show that it reduces to the following formula, and now this is a finite sum. This is much easier to do. Another way of looking at this is more like graph theoretic, is I'm going to let Cameron have C M&Ms and Kayla have K M&Ms. It's always good to choose good notation so you can just quickly glance down and see what's going on. And so I'll use C for Cam, K for Kayla, so I can quickly look down and see what's going on. So there's 3 possibilities. I can go from CK to C-1, K-1, each person eats an M&M. I can go from CK to C-1K, or from CK to CK-1. And each of these happens 1/3 of the time. And so I'm going to show this as a tree. And I'm going to use arrows to indicate the 3 possibilities. So from each vertex, there are 3 arrows coming out. So for simplicity, I'm going to look at the M&M game when each person starts with 4 M&Ms. We start at the top at 4-4. We want to end at 0-0. So the only way to get to 0-0 is we've got to be at 1-1. Cam and Kayla each have to have 1 M&M, and then they both have to toss heads. So I just need to figure out what's the probability we get to 1-1. And so we basically just want to count the paths. And so if we start at 4-4, 100% of the probability is there. And then one turn later, 1/3 of the time we're at 4-3, 1/3 of the time we're at 3-3, 1/3 of the time we're at 3-4. Now that we're at those 3, we can look at what happens. And so for 4-3, we can go to either 4-2, 3-2, or 3-3, and so on and so on and so on. And you can see the probability flows. So 2 of the arrows out of 4-3 bring me to the next level. And then 1 of the arrows increases the probability at 3-3. Similarly for 3-4. And then I look at what happens from 3-3, noting that some of 4-3 and 3-4 went there. And I now get the probability for being in different places in the next row. And then just lather, rinse, repeat. I now look at what happens with 4-2 and 2-4, with then 3-2 and 2-3, and so on and so on. And you can just keep going through and just keeping track of all the probabilities. and you get the wonderful number 245 over 729, and then 1/3 of the time from there, I'll then get to 0, 0. So how can we interpret this? Well, hopefully you've seen recurrence relations. So I am honored to be the president-elect of the Fibonacci Association. If you ever have any needs for Fibonacci numbers, please let me know. We have a conference coming up in just a few weeks at Harvey Mudd College. And so the Fibonacci numbers are typically defined as each one is the sum of the previous two, and we start the sequence with 0, 1, 1. And it turns out you can prove that there's a closed form expression for the nth term of this sequence. So I don't have to keep adding from scratch. I can just jump to whatever term I want. And that's great. It's nice when you have a closed form expression like this and you don't have to compute from the very beginning. It turns out that it's not just the Fibonacci numbers, but a whole class of recurrence relations like this have closed form expressions that allow you to just jump to any term in the sequence. Well, what we have is we have something a little bit more complicated. If we let XCK be the probability of a tie when Cam has C M&Ms and Kayla has K M&Ms, we get a recurrence relation, but now it involves something with two indices rather than just one index. So hopefully, at least the college students and higher, you've seen recurrence relations like the Fibonacci numbers with one index. How would we solve something with two indices? 1/3 of the time, we lose one for each. 1/3 of the time, just Cam loses. 1/3 of the time, just Kayla loses. This is basically just the tree we saw earlier, but rather than drawing all those pictures, I can just write it down algebraically. Well, I can write it down algebraically if I was smart enough to see that this is the recurrence relation, that I can throw away the possibility of both of them getting a tail and not eating. What if I didn't see that? Well, if I didn't see that, the following recurrence is the more natural one, where now each option happens 1/4 of the time. And notice 1/4 of the time, I get what I started with, XCK. So if I then subtract that, I would get 3/4 XCK equals 1/4, yada, yada, yada. And then when I multiply by 4/3, I see, oh, there is the simpler recurrence. And so if we weren't smart enough to see it in the beginning, when we do the algebra, it actually shows something interesting is going on, and one of the terms vanishes on the right-hand side. So let's say we wanted to solve this recurrence. So I don't want to go through the details of how you would try to solve a recurrence relation with two indices. I'll just show a nice simple way to do the algebra. We know if neither one of them has an M&M, it's a tie, so x00 is 1. We know x10 and x01 is 0, because if one of them has an M&M and the other doesn't, then it can't be a tie. And then we use the recurrence relation to calculate x11. And we know that that's 1/3 x00 plus 1/3 x01 plus 1/3 x10. And now we know x11 is just 1/3. And then we can now calculate what goes on when the largest index is a 2. We know x20 and x02. We then calculate x21, which is the same as x12. And to calculate x21, we only need to use things where the largest index is a 1. Now that we know that, we can then calculate x22 and we get 5/27, and so on and so on. So even if we don't write down the explicit formula for the solutions, we can write down an algebraic relation that allows us to very quickly calculate. So the next thing is to try an easier problem and build up some intuitions. So in the interest of time, I'm going to skip this. It is related to Catalan numbers. I'm not going to go into all of that, but there's a lot of wonderful, wonderful connections. What I want to do now is talk a little bit about how do you find some of these connections. So here are the probabilities of the tie. 1/3 when k equals 1, 5/27 when k equals 2, 11/81 when k equals 3, and so on and so on and so on. Does anybody see anything interesting about either the numerators or the denominators? Does anybody notice any pattern?
The denominators are powers of 3.
Yeah, it looks like the denominators are powers of 3. Now, one of the things is we may be writing the wrong powers of 3, because unfortunately, when you do a lot of calculations, sometimes it automatically reduces things. So maybe the 1181, maybe that's really supposed to be 33 over 243, and it just was reduced into lowest terms. So my advice is if you're ever trying to figure out what a pattern is, do not simplify the expressions. So if we multiply by 3 to the 2k minus 1 to clear denominators, we get the sequence 1, 5, 33, 245, 19, 21, and so on. That sequence meant nothing to me, but I know of a beautiful website called the OEIS, the Online Encyclopedia of Integer Sequences. And if you give it a string of integers, it will tell you every sequence it knows where that string occurs. And so when I fed that in, it spit out that it was sequence A084771. And if you go to that sequence, it starts listing, all the properties it knows about it. It lists references, it lists relations. It's the coefficients of one of this, there's so many interesting things it can give you. If you've ever done proofs by induction in mathematics, you frequently know that one of the hardest things is to try to figure out what are you trying to prove. And if you are able to gather some data and feed it in, you can use this to get a sense of what you should be trying to prove. And that often helps you figure out what methods to use, what calculations to do. All right, so we've got a few minutes left, so I want to just end with a few quick takeaways, as well as some comments about some future work. I have hopefully some of my Polymath Junior Summer students, on the Zoom talk right now, and they're going to continue investigating this problem. And so here are some possible future problems. And so I was fortunate enough to be sitting next to April at a conference at Texas State in early June. And we were chatting, and the conversation came to some of the things I had done with my kids. And I told her about the M&M game, and we came up with some interesting generalizations. And hopefully by the end of the summer, we will be able to report back on answers to these problems. So what if each person tosses several coins simultaneously, and the coins have different denominations? What happens in a situation like that? How does that affect these probabilities? What if some of the coins are positive and some of the coins are negative? And what if you have a starting value? So for example, maybe one coin is a +5 and then we have a -3 and a -2. Does it matter if we do it like that versus a -5 and a +3 and a +2? They both have the same average. Does it make a difference if the larger one is the positive or the negative? And so I did not play hooky from the conference. I did not move off and work on this problem while other people were speaking, but we did have a coffee break. And during the coffee break, I quickly wrote down a few commands in Mathematica. I was not trying to program most efficiently. I was just trying to quickly write down a program to run. And so this gives me a simple function where I put in the starting value. How much money do I want to assume? I put in the values of 3 coins, and then just how many times I want to keep playing, and it will tell me whether or not somebody actually hits 0. And so I put in 1,000. I put in my coins as -5, 3, and 2, and I said toss up to 200,000 times. And for each toss, we're going to toss 3 coins. If the first is a head, we subtract 5. If it's a tail, we do nothing. If the second is a head, we add 3. If it's a tail, we do nothing. If the third is a head, we add 2. If it's a tail, we do nothing. Does anybody notice anything strange about the plot? Anything look a little strange about this plot?
It seems to get less noisy around 100,000.
Yeah, the reason it's getting less noisy is because it was taking a long time for Mathematica to display it because I was saving so much data. So if you look at the code, it says, if n is less than 100,000, add the result to the list. If n is greater than or equal to 100,000, then only add every thousandth. And so I'm only adding 1,000th of the data. So that's why it's looking less noisy. It was just causing some issues in terms of how things were going. So here, we survived quite a while, 135,260. There's a lot of good theory that predicts based on what these numbers are, how long you should survive based on the starting value. How long do we expect you need to go before you will finally decay? But can we say something about what's the probability of a tie? And so these are just two of many possible questions. And just to summarize and give a couple of takeaways, this began years ago with a question my son asked me, and the new project is coming from a conversation over dinner. I love to multitask. I love to be trying to do many things at the same time. It's the only way I can be as productive as I am. I'm always looking for interesting questions, questions of different levels. And what's great is these are questions that you can explain very easily. I'm not using advanced calculus. I'm not using powerful graduate level mathematics. I'm tossing coins and I'm asking, when do things align? And in doing so, it turns out a lot of really interesting mathematics emerges. So even though this might have seemed like a silly problem, the hypergeometric function emerges, infinite sums and memoryless processes to reduce them to finite emerges, generalizations of Catalan numbers and walks on graph, so many things, multidimensional recurrence relations. So from very simple mathematics, questions, very complicated techniques and methods arise. In terms of trying to look at the data, it's important to try to find what's a good way to look at it. And for many things, if you can find the right way to look at a problem, you have a much better chance of being able to understand it. When we looked at the data, if we looked at all the data from 1 to 110, the fit wasn't perfect because it took a while for things to settle down. If we looked at from 50 to 110, it was really good. Also, we weren't looking at the data, we were looking at the log of the data. And by doing that transformation, it was presented in a way that was a lot easier to look at. So what I thought I would do, since I still have a few moments, is I love doing Rubik's Cubes. And so I thought I would show you some of my favorite Rubik's Cubes. I'm going to hopefully turn on the video. Okay. And so let's see. Is everybody familiar with a standard Rubik's Cube? Everybody has seen a Rubik's Cube? Okay. So what I want to do now is show you two of my favorite. So the first one, can you see this one? All right. I love this one because when most people say they do Rubik's Cubes, you say, oh, what kind of cubes do you do? Oh, you do something with 6 sides. Wow, I do 12 sides. It turns out this is really the same as a 6-sided cube. It's just the way it's constructed, it looks a little bit different. There's 4 corners. This is the red, white, blue corner. Trying to do it so where's the camera? So it's really the same as a 2x2, but the way it's constructed, it makes it look like it has 12 sides, not 6. This is another one of my favorite cubes. No, actually, no. This is my second favorite. Let me grab the one. Give me 1 second. I pulled the wrong one out of my backpack. If I can't find it, I'll use that one instead. All right. Yeah, here. Okay, good. Pulled the wrong one out. That was my second favorite. This is the one I really like. So you have like an X pattern on the top. Okay, but it's still, in some sense, 3x3. But if you look at the sides, it's 2x3, not 3x3. So this one looks really strange. If you try to turn the red side, it doesn't turn. This is basically the same as a 3x3x3 cube if you hold it the right way. If you hold it at a 60-degree angle, there is your face. And you can now see it's 3x3. So if you look at it the right way, it's really the same. But you have to look at it the right way. This is not the corner. This is actually the middle. These are the corners. And so much of mathematics is, can you find the right way to look at something? And so once you find the right way, things are very easy. And then the last thing I'll just end with is the best piece of advice I've ever heard in my life. And so this is called the law of the hammer. There's lots of different variations of it. My favorite formulation is if all you have is a hammer, pretty soon every problem looks like a nail. So there's 2 ways to look at this. One way is if you have a hammer, whatever they give you, you're going to try to make it look like a nail so you can use your powerful technique. There is a debate going on tonight. I am not listening to it right now. I am sure whichever candidate is asked a question, they have some prepared speeches that they want to give, and they will take whatever question you give them and they will migrate it to what they want to talk about. So if you are really good at something, you try to find a way to use what you're good at to solve it. But a better way of looking at this quote is go to the land of the screwdriver. If they could have solved the problem with the screwdriver, they would have. They're smart people. So if you want to make a name for yourself, if you want to make a contribution, if you're looking at the same problems as everyone else who's had the same training as you, it's going to be very hard to make a major contribution. If, however, you take your training and you go to a completely different field, if they could have solved the problem with their techniques, they would have. And so I've written papers in accounting, in marketing, in statistics, in sabermetrics, in economics, in computer science, geophysics, so many different areas, because I've been able to take some techniques I've learned in number theory and probability and combinatorics and apply them in very different ways. So right now, you're in an REU. You are taking a stab at doing some research. You all have different backgrounds. You've all seen different things over the years. So these paths that you've taken have led you to a different set of tools. And so sometimes we have a good idea of what's a good tool for solving a problem. Sometimes we even know what the problem is. But a lot of times, what you learn in one area can be a wonderful guide in another. And just encouraging you to, keep open minds, to try to see, what could you throw at this that other people haven't? Why haven't people been able to solve this? What new results have come out in the last few years? What new perspectives? Is this related to something you might have seen someplace else? So hopefully I will get a chance to, I know I met some of you at the conference. Hopefully I can meet some more of you at some of the conferences at the end of the summer or the joint math meetings. I'm always happy to chat. If anybody has any questions, happy to talk now for a little bit. So thank you.